Hello, my name is Sylvie Leguyader, and I am the manager of the lifestyle imaging facility at the Karolinska Institute in Sweden. In this tutorial, you will learn how filters used for fluorescence microscopy work, what bleed-through is, and how to deal with these problems. Detectors used to acquire images of fluorescence samples usually are black and white detectors. The reason for this is that black and white detectors are a lot more sensitive to low light levels than color detectors. Color detectors are only needed for colored samples that are not fluorescent, for example, samples labeled with beta-gal or DAPI. Some wide field microscopes are equipped with color cameras, but most of them have black and white cameras. All confocals have black and white detectors. When we acquire an image with a black and white detector, all the photons that reach the detector participate to the image. We then assign an artificial color to this image, for example, green, if we think that the signal comes from FITC. If the sample only expresses FITC, there is no doubt about where the photons came from. However, when imaging a sample labeled with several fluorophores, we must acquire several black and white images, and then assign artificial colors to them. But how can we be sure that all the photons that participated in the green image, for example, indeed came from FITC and not from the red fluorophore? Often the photons coming from one fluorophore show up in the image of another one, and this is not detectable in the black and white image. This condition is called bleed-through and can lead to dramatic interpretation errors. To explain how we image multicolored samples using black and white detectors, we will start with the example of a wide field microscope, then show that the same principles with minor changes apply to confocal microscopes. Bleed-through also has other names like crosstalk or crossover. All these terms refer to the same emission problem. Photons from two fluorophores participate to a single black and white image. Cross-excitation, on the other side, is an excitation problem, where two fluorophores are excited by the same excitation light. Cross-excitation and bleed-through prevent us from separating the signals coming from the two fluorophores in our sample. As an example, let us consider the case of a triple labeled sample containing DAPI, FITC, and TRITC. First, we must find the full excitation and emission spectra for each of these fluorophores. You can find the spectra in several ways. Use online spectra viewers like those on the BD or the Invitrogen websites. Some fluorophores like M-Cherry, for example, are not listed on these websites very often. In that case, go online and do an image search for M-Cherry spectra. Make sure you are indeed looking at the correct spectra. You can also find the original article describing the fluorophore. Or you can look at the specification sheet of the fluorescent dye on the website of the company you bought it from.
So the first thing we will do in the workshop is that we will find all the spectra of all the fluorophores that you have in your sample, including any nuclear dye. And that is the spectra, not only the excitation peak and the emission peak.
Let's go back to our example. Here are the excitation and emission spectra of the three fluorophores in our sample. For each dye, two curves are shown. The line on the left is the excitation spectrum, and the line on the right is the emission spectrum. When the fluorophore is excited, it absorbs light at wavelength, shown by its excitation curve. The electrons in the fluorophore get excited and they start vibrating. These vibrations lead to a loss of energy. The molecule then goes back to a more stable state by releasing energy in the form of a photon. This is fluorescence. The emitted photon has a lower energy than the absorbed photon because of the energy lost in the vibrations. This is the reason why the light emitted is shifted towards the right side of the spectrum, towards longer wavelengths, which are less energetic. Therefore, the light used to excite blue fluorophores is in the near UV. The light that excites a green fluorophore is blue, and the light that excites a red fluorophore is green. So similarly, to excite far-red fluorophores, we use red light. If we excite a fluorophore with a wavelength close to its excitation maximum, the fluorophore starts emitting photons at different wavelengths. Most emitted photons are near the emission peak, but really, the fluorophore emits a whole range of wavelengths. If we now change the excitation wavelength so that it is not optimal, less photons are emitted, but they cover the same range of wavelengths. The recorded intensity is only lower. Therefore, regardless of which wavelength we use to excite it, the fluorophore will always emit all the wavelengths shown in its emission spectrum. When imaging a sample with multiple labels, we use filters to discriminate the fluorophores. On wide field systems, these filters are often organized as a set in a filter cube. A filter cube contains a set of 3 filters: an excitation filter, a dichroic mirror, and an emission filter. All 3 types of filters are required when the light used to excite the fluorescent sample comes from a lamp that emits white light. Typical examples of these lamps are mercury and metal light lamps. In our example, the filter cube used to image green fluorophores like FITC has the following specifications. The lamp emits white light, which travels through the excitation filter. The excitation filter is specified as 470/40. This means that it transmits 470 nanometers plus minus 20 nanometers. In other words, the filter absorbs all wavelengths outside of the 450 to 490 nanometers range. This is in the blue part of the visible light spectrum. Such a filter with a specific range is called a bandpass filter, often abbreviated as BP. Only the blue light needed to excite FITC is transmitted. The excitation light then reaches a dichroic mirror, which is placed at a 45-degree angle. The dichroic mirror is specified 500 LP. LP stands for long pass. This means that the dichroic mirror splits the light in 2 parts. It acts as a mirror for wavelengths longer than 500 nanometers, while shorter wavelengths go through the dichroic mirror. Our excitation light is shorter than 500 nanometers, so it travels straight towards the sample. Now, looking at the specifications of the excitation filter and the excitation spectra of the 3 fluorophores, we will answer the following questions. How efficiently do we excite FITC with this excitation filter? Are DAPI and TRITC cross-excited, and if yes, to what level? The yellow rectangle represents the filter. We need to look at the part of the excitation spectrum that fits inside the filter. The answers to our questions are that DAPI is not cross-excited by light going through this filter. FITC is very efficiently excited. And TRITC is a little bit cross-excited. So when we use the green filter cube, both FITC and TRITC are excited and start emitting light. The light emitted by FITC and TRITC is longer than 500 nanometers, so it is reflected by the dichroic mirror towards the emission filter. Additionally, the excitation light is partially reflected by the cover slip. This strong reflected light is shorter than 500 nanometers, so it travels through the dichroic mirror and is not reflected towards the detector. It gets lost in the microscope. So far, we have not been able to separate the light emitted from our 2 fluorophores. We must make sure that the emission filter does the job. Now, looking at the specifications of the emission filter and the emission spectra of the 3 fluorophores, We will answer the following questions. Which wavelengths are transmitted through the emission filter? How efficiently do we collect the light emitted by FITC? Does the weak emission coming from TRITC bleed through the emission filter, and if yes, how much? The emission filter is specified 540/60. The answer for the first question is thus that the emission filter transmits light from 510 to 570 nanometers. Let's now see how much of each emission curve fits into the filter. We see that a lot of the light emitted by DAPI is collected through this emission filter. However, we have identified earlier that DAPI is not excited through our excitation filter, so it does not emit any light. Our emission filter collects about 80% of the light emitted by FITC. This is the fluorophore we want to image, so it is very efficient. We also see that the TRITC signal bleeds through this filter a little bit. We have seen before that TRITC is inefficiently cross-excited by our excitation filter, and we see here that the bleed-through is rather small. So we expect the emission that reaches the detector to be quite weak. We have now identified that the FITC filter cube leads to both cross-excitation and bleed-through of TRITC, but at a low level. If the FITC signal is much brighter than a TRITC signal, we can safely image FITC. The participation of the red photons to the green image will be negligible. However, if FITC is very weak, we will need to push the intensity of the lamp and the exposure time to image it. In these conditions, and if TRITC is very bright, the red signal will significantly influence the red image. In this case, the solutions are to either change the filter set or change one of the fluorophores. Thus, bleed-through is not just about matching the fluorophore spectra with the filters. It also depends on the relative intensity of the fluorophores. After imaging FITC, we need to change the filter cube to image DAPI, then TRITC. Once more, we must answer all the following questions for each fluorophore. How efficiently do we excite each fluorophore? Are the fluorophores cross-excited, and if yes, to what level? How efficiently do we collect the emission from each fluorophore? Is there any bleed-through of one fluorophore to the other channels? Is one fluorophore much stronger than another, which increases the risk of bleed-through? So far, you have learned how we can acquire color images with multicolor samples using black and white detectors, the role of each filter inside the filter cube, where to find the spectra of your favorite fluorophores, how to check the efficiency of excitation, the amount of cross-excitation, the efficiency of emission collection, the amount of bleed-through. So far we were considering the case of a wide field system. We will now show that the same principles, with only minor changes, apply to confocal microscopes. Confocals do not use white light lamps as excitation sources. Instead, they use lasers, which emit colored light. Lasers have a very narrow bandpass of only 2 to 3 nanometers, so there is no need for excitation filters when using a confocal. For example, this confocal is equipped with 4 lasers. We will use 3 of them to excite our fluorophore. As seen before, we will excite DAPI with the near UV 405 laser. We will excite FITC with the blue 488 laser. We will excite TRITC with the green 561 laser. As in a wide field system, the excitation light from the lasers reaches a dichroic mirror. Because on a confocal system, it is possible to turn on several lasers at the same time, the dichroic mirror allows several wavelengths to reach the sample. Thus on the confocal, we must select a dichroic mirror specified for all the lasers that you want to use. In our example, we will use this dichroic mirror. However, this one would also work, even if we do not use the 640 laser. Here again are the excitation spectra of our three fluorophores, DAPI, FITC, and TRITC. As in the previous example, the first question we need to answer is, are the fluorophores sufficiently excited by the lasers? The 4-5 laser is used to excite DAPI. As you can see, we excite DAPI very inefficiently, at only a few %. Nevertheless, DAPI is extremely bright, and even when excited so inefficiently, it will emit brightly across its emission spectrum. The 488 laser excites FITC very efficiently, at around 80%. The 561 laser excites TRITC very efficiently, at 90%. So the answer to our first question is that these three lasers will sufficiently excite our fluorophores. The second question we ask is if the fluorophores are cross-excited. Is DAPI excited by the 488 and the 561 lasers? No, it isn't. Is FITC excited by the 405 and the 561 lasers? Yes, FITC is excited by the 405 laser at around 5%. Is TRITC excited by the 405 and the 488 lasers? Yes, the 488 laser excites TRITC around 10%. Thus, the answer to our second question is that we have several cross-excitation issues with these fluorophores and these lasers. Back to our example. The three lasers we have chosen are now on simultaneously, so the three fluorophores start emitting light at the same time. The dichroic mirror sends this complex emission light towards the detectors. The emission light then reaches secondary dichroic mirrors. These are long-pass filters that work exactly as the dichroic mirrors found in filter cubes. The emission light is split in two parts in front of the detector. The blue light below 495 nanometers is sent towards the first detector, whilst the rest continues towards the other detectors. The green light below 560 nanometers is then sent to the second detector, and so on. Additionally, each of these emission lights goes through emission filters, similarly to what happens in filter cubes. And here, you can see a summary of the whole light path, showing lasers and filters. Because the three fluorophores are excited and emit light simultaneously, we will now try to make sure that these emission filters transmit what we want and remove what we do not want. To do that, we first need to answer the third question. Do the emission filters we chose allow us to efficiently collect the emission light for each fluorophore? To answer this question, we consider what part of each emission curve fits into each emission filter. If we look at the emission filter and emission spectrum for DAPI, we can see that less than half of the light emitted by DAPI is collected through this filter. However, for FITC and TRITC, we are collecting light more efficiently, around 70 to 80%. Thus, the answer to our third question is that these filters work very well for our three fluorophores, although we throw away a lot of light of the DAPI emission. This is because DAPI is not a very good blue fluorophore. It actually emits blue, green, and red light. We're only interested in the blue part. Never just assume that the filters on your microscope will work with your fluorophores. It often happens that the available filters are far from optimal. Here is an example of M-Cherry seen through the same emission filter. Both TRITC and M-Cherry are red, but M-Cherry is redshifted. Thus the 570 to 620 filter works well for TRITC, but it collects less than 50% of the light emitted by M-cherry. Always check your emission filters before you choosing a fluorophore. This problem is especially frequent for red and far red fluorophore, as their emission spectra vary greatly. Our fourth question asks if the emission filters we use allow us to efficiently remove the emission light coming from the other fluorophores in our sample. Does DAPI bleed through the green and the red emission filters? Yes, it does quite a lot, about 20% in the green filter and 5% in the red filter. Does FITC bleed through the blue and the red emission filters? Yes, it bleeds through the red filter around 10%. Does TRITC bleed through the blue and the green emission filters? Yes, it bleeds a little bit through the green filter, maybe 2%. Thus, in this example, we have bleed-through issues with several of our fluorophores. We have seen before that on the wide field system we imaged the 3 fluorophores one at a time, each time changing to the corresponding filter cube. This is because wide field systems usually only have one light source and one camera. This is called sequential imaging. On confocals, however, we have several lasers and several detectors. We can gain time by turning on all the lasers and detectors at the same time. This is called simultaneous imaging. Since all the fluorophores are excited at once, they emit light at the same time, and we can now image them simultaneously. This imaging strategy has the advantage of being fast, but any bleed-through issues will become a real problem because all the fluorophores are very well excited. In our example, we have seen that we have quite a few bleed-through issues. This means that we should not image the 3 fluorophores simultaneously. We need to image them sequentially instead. We will first excite DAPI with the 405 laser and collect its emission in the first detector. Then we excite and image FITC by turning on the 488 laser and the second detector. And finally we image TRITC with the third laser and detector. Sequential imaging helps avoid bleed-through, but the acquisition of the 3 images takes 3 times longer. To gain time and still avoid bleed-through, we can sometimes decide to image the problematic fluorophores sequentially, while still combining those that do not have any bleed-through issues. In our example, the light emitted by DAPI bleeds through the red filter a little bit, but if TRITC is strong enough, the contribution of the DAPI bleed-through to the red image will be small, and we will be able to combine the imaging of DAPI and TRITC, and then image FITC on its own.
You have now learned how to select the correct laser, direct mirror and emission filter for your fluorophores. You have also learned how to choose an appropriate strategy between imaging simultaneously, which saves time, and imaging sequentially to help solve bleed-through issues, and how sometimes it is possible to combine channels.
Unfortunately, imaging sequentially does not solve everything. Sequential imaging works very well to solve issues with bleed-through, but no cross-excitation. However, the light from fluorophores that are concerned with both cross-excitation and bleed-through will show up in the wrong channel, even during sequential imaging. That is because our fluorophores that we do not want to image is excited by the wrong laser, so it starts emitting, and at the same time, its emission is not cut off by the emission filter. And the problem, as we have seen, is worse if the fluorophore that bleeds through is much brighter than the one we want to image. So if we go back to our triple labeled sample, DAPI strongly bleeds through to the green image and a little to the red image. However, DAPI is not cross-excited by the lasers used in the other 2 channels, so we can image safely. And we know that DAPI will not participate to the green and the red images. However, TRITC bleeds through to the green channel and at the same time it is cross-excited by the 488 laser. So if we image FITC on its own, in sequential imaging, we know that TRITC is excited and bleed through. If FITC is much brighter than TRITC, this is not a problem, and the red signal will have a very small contribution to the green image. However, if TRITC is much brighter than FITC, imaging sequentially will not solve the problem, and we must then use another strategy. As a summary, when designing your experiments and before preparing your sample, make sure your combination of fluorophores matches the excitation, wavelength, and emission filters available on your microscope. Then decide if you can image simultaneously, sequentially, or if you can combine channels. If none of these solutions work, you might need to use a confocal with a spectral detector. You can learn about this function in another video. In this tutorial, you have learned about matching the fluorophore spectra with the microscope filters. This is the basis of microscopy. You now understand why it is very important to consider the whole spectra of fluorophores, not just their excitation and emission maxima. You also know how filters allow us to discriminate the signals coming from several fluorophores, while still allowing us to use sensitive black and white detectors. And you have learned how to identify the risk of cross-excitation and bleed-through, and how to avoid these problems. Remember to check these 5 points every time you use a new fluorophore, or if you change microscope or microscope filters. How efficiently do we excite each fluorophore? Are there any potential cross-excitation issues? How efficiently do we collect the light emitted by each fluorophore? Are there any potential bleed-through issues? And is any of your fluorophores likely to be much brighter or much dimmer than the other fluorophores in the sample? Do this regardless of whether you use a wide field system or a confocal system. Check all these points when designing your experiment before buying your fluorophores. Thank you for your attention.